So now let's take a look at another way to solve the same problem that we just did. So in this way, this is called the subtractive method. And we're going to use the exact same equations as we did before in our earlier example, but we're actually going to use fewer shapes. And the parts that we are going to treat differently are the parts that are cut away. We're going to call those negative areas. And you'll see what that means as we go through the example. So here you see that exact same shape. Basically it starts off as a 6 by 6 square. We want to determine that reference axis, and our square is going to be shape 1. Shape 2 then is going to be our triangle, and it's going to be a right triangle. Well, just like we did before, the first step is to look at the area for each of the shapes. So in this example, shape 1 is our square. That's just width times the height. That's 36 inches. Shape 2, we want to know the area of that rectangle, but since it's removed or it's cut away, we're going to call it a negative area. And there it's the same formula, 1/2 the base times the height, but since we are cutting it away, we're going to put a negative sign in front of that. That's going to be minus 4.5 square inches. So using that exact same process that we did in the last clip, we want to determine the centroid location for each of the individual shapes. So for shape 1, that is located right in the middle of the square, the 3 by 3. And for shape 2, this is where we have to be careful. So remember, it's 1/3 base times 1/3 the height, but we've actually moved it from our original example. The base is still referenced to the horizontal, and the height is still referenced to the vertical or the y-axis. And notice where we're measuring from. In this case, we're measuring from the upper right corner. That's where the right angle is. That's important. That's kind of one of those gotcha moments here. So I want to make sure that you see that. We're measuring the distance of the centroid from the upper right corner. So as in our last example, what we want to do is determine the x and y coordinates for the centroid for each of the individual shapes. So for shape 1, our big square, our x component is just 3. Our y component is, so we have 1/3 the base, which is 1/3 of 3, that's 1 inches. That's 1 inch over from the far right. So that turns out to be 5 inches from our coordinate, our y coordinate. That's how we get 5. So let's look at that again. We're looking at 1/3 of 3, which is 1, and that we subtract that from the 6 to get 5. So for our y coordinates then, for shape 1 we get 3, and for the triangle it's 1/3 of 3, which is 1. That's down from the horizontal part on top. So that actually turns out to be 5 inches also. Then, just like we did before, we want to create a table and multiply our individual areas times the individual x component for the centroid of the individual shapes. So we take 36 times the 3 for shape 1 in that first row, and we get 108 cubic inches. And here in shape 2, remember we're cutting it away, so we're considering that a negative area. and we get minus 22.5. Do the same thing for the y's, and we get 108 cubic inches again, and minus 22.5 cubic inches for y. Looking at the numerator, we take those products and we add them together. So when you add a negative number, you're really subtracting. So 108 minus 22.5 gives us 85.5. And that's true for both x and y. If we then look at the denominator where we are summing or adding the areas, again, remember this is one of those gotchas. Because it's a negative area, we've cut it away, we have to subtract that area. So the area of the square is 36 square inches. We subtract the area of the triangle, and we end up with 31.5. Finally, we have our numerator and our denominator, and we go through the same process, and lo and behold, we get the same answer. 2.71 for x bar and 2.71 inches for y bar as well. And just like before, it's still symmetrical. So you can see we solved the same problem two different ways. With the positive method, we had three shapes and we added everything. For the negative method, we had two shapes, but the kind of the tricky part there was that we have to remember to subtract the areas. In all of our summations, we have to subtract all those things. You get it. So what we just did was we used these formulas and two different methods to calculate and get the same answer for a complex shape.